This will be the last video in this particular section before we move into inverse trig functions. But this is another important setup for later in the semester when we talk about trigonometric identities. And I wanted to talk about the basic, or what we often refer to as the fundamental trigonometric identities, because these are like the building blocks we're going to be using when we get into analytic trigonometry, which is one of the big parts of the 5th exam. So for this upcoming exam, number 4, it's all more focused on basic trigonometry, which is a lot of what we've been doing. Graphs, domain, evaluating, unit circle, and triangles, which we're going to get into very, very shortly. But the first of the fundamental identities are what are called the reciprocal identities, which revert back to the definition. And these are ones I discussed when we were talking about the graphs of secant and so on. But basically, each trigonometric function is the reciprocal of a different trigonometric function because of the definition. So on the packet, I referred to the definition because notice that, well, sine was defined to be y, cosecant was defined to be the reciprocal. So by fundamental definition, cosecant is one divided by sine always. And also, I wanted to review what is an identity. What does that word mean? But an identity is always an equation in mathematics which is always true. So, like for example, a simple identity would be x plus x equals 2x, right? Because we know that if we have 2 plus 2, it's always going to make 4. It's going to be double the amount. Like say 7 plus 7 is 14. It's an algebraic identity. It's just it's something that is true because it has to be. Or say another example, like x times x is not 2x, it's x squared, because that's what x squared is defined to mean, is when you repeatedly multiply x's. But those are some examples of basic identities, which are true always. Trigonometric identities, now notice that, for example, with the cosecant of t, this is still always defined to be true, but sometimes, like cosecant, it's not always defined. So when, because secant is 1 divided by sine, there are some points where that would be undefined. But it's okay. It's still true because cosecant is not defined at those specific points where sine is as well. Additionally, secant, cosine was defined to be the x point on the unit circle related to the distance. Secant is the reciprocal of cosine. It's 1 over x. So another fundamental definition stemming from a fundamental identity which stems from the definitions is that secant must be 1 over cosine of t. Again, this doesn't necessarily just apply to t, but any variable that you would throw into it. We just use t in the packet because I think it makes a lot of sense. But if it was secant of x, it would be 1 over cosine x, just like we were doing when we were graphing them. And then tangent was defined to be x over y. But technically, we could also define tangent by using sine over cosine, because, and I did this when we were talking about tangent, because tangent is y, well, sine of t is always y, and cosine of t is always x. And that's one way to write the tangent function using sine and cosine, where cotangent is x over y. That would be cosine over sine instead. But actually, additionally, cotangent could also be described using 1 over tangent. I did that in the previous, because since tangent was sine over cosine, if we reciprocate 1 over sine over cosine, it flips it back. But technically, tangent is also the reciprocal. This is just another basic property of reciprocals, is that if you take the reciprocal of a reciprocal, it flips back. Because say, for example, I have 2/3. I want to take the reciprocal of that. That's 3/2. If I take the reciprocal again, it goes back to 2/3. It's cyclic. Not in the same way as sine and cosine, but the reciprocal identities apply both ways. So tangent is 1 over cotangent. Cosecant is 1 over sine. But additionally, sine is 1 over cosecant. They are reciprocals of one another, because I could take this identity, flip both sides of the equation, and that would lead me to a new identity based on algebra, which would be 1 over cosecant is equal to sine. But basically, all of these fall along the lines of reciprocal identities. There's a connection between them, which is easy. And the memory trick for this, which I said before, but I'll reiterate now, is that sine and cosecant are reciprocals of one another. They both flip each other. Cosine and secant are reciprocals, tangent and cotangent. It's easy to remember because they're never paired with the same letter for reciprocals. It also has nothing to do with the cofunctions. That's a completely different set of identities, which we're going to get to when we get into analytic trig later. But the last fundamental identity, which is worth covering now, is what are called the Pythagorean identities, which stem from the Pythagorean theorem. But going back to the unit circle, recall that if you remember when we were talking about the unit circle, I emphasized the importance of the unit circle equation, which was the fact that the equation itself of the entire circle was given by x squared plus y squared equal to 1, because that's how a circle is when its radius is 1 and it's centered right there at the origin. It must have that equation. But that being said, all of the trigonometric functions are always bounded to this fundamental formula, because each point, each part of the trigonometric function always must line up on the circle. So it always must be a part of this equation, if that makes sense. But also, kind of reverting back to this, what was helpful to remember from the last video is that cosine is really the x value on the unit circle, sine is the y value. So if we actually just substitute those in, those must also remain true, because sine and cosine are always fixed to the unit circle, conceptually, if that makes sense. But basically, if we actually just substitute those in, that's what it's, part 1 says to do, plug the appropriate functions into the unit circle equation. What that would leave me with is, well, cosine is x, so let me just recopy down. What I have is that x squared plus y squared must be equal to 1. If I substitute in, well, cosine of theta, or cosine of t if you prefer, it doesn't matter the variable I choose, is x. So if I square that, and then plus y squared, it must be equal to 1. And this is a fundamental identity that if you've taken trig before in high school or wherever, you probably remember hearing about this one. And if not, that's fine. But this is another identity which is kind of weird. It seems strange, but it must be true based on the Pythagorean theorem. And really, if I look at the triangle a squared plus b squared must be c squared, that's another way to make sense of why this must be true. Also, it's worth mentioning that how we write it with trigonometry is we often will shorthand a square function by putting it on the function, which just indicates a different way of writing it. The reason why we put it here instead is that, because if I was to write this cosine theta squared, the problem is in ambiguity, kind of like I was saying a few videos ago. The question is, where's the square? Is the square on theta, or is it on the whole function? If we write it like this, usually what that implies is cosine theta squared. That is totally different than cosine theta quantity squared. And what I have here is cosine theta quantity squared, because I'm substituting it in, and of course the whole thing must be squared. But nonetheless, anyways, this is it. Again, this is, oops, did not mean to have the eraser there. This is a fundamental identity. This is always true no matter what. And it also allows us to connect sine and cosine together based on squares. We're going to see how this helps later, but for now, I just want you to be aware that all of these different identities exist. And they're kind of just like algebra formulas that relate all of the different trigonometric functions together. And it turns out there's 2 more versions of these for the other 4 trigonometric functions as well, which also stem from the unit circle, which I wanted to show you real quick as we wrap up this very long lecture. So I don't know who joined my board. That is unusual. But if I take, so if I start with the unit circle equation, because again, that's the moral of the story for these identities, is they all still have to satisfy this equation, because each point must satisfy the equation. But notice that if I take this equation, let's say I was just to divide through by x squared as it says to do, meaning I'm going to take both sides, divide by x squared. And remember, that would have to divide each term by the rule of division within an equation. what would happen here is that notice, well, x squared over x squared would become 1 because anything divided by itself. What I would get here is y over x squared. I could also rewrite that as y over x quantity squared. And on the right-hand side, 1 over x, I could write that as 1 over x quantity squared as well by rule of fractions, because 1 squared is 1. But what I wanted you to notice is that it takes that equation and it shifts which trigonometric functions we're looking at. Because, well, y over x, we know that to be the tangent function, and 1 over x to be the secant function, because that's reciprocal of cosine, because cosine is x, and reciprocal of cosine is secant. But my point is then those are two of the other specific functions by definition, and I could go ahead and substitute that in, because y over x is equal to the tangent function, and 1 over x is equal to the secant function. But this gives me another version of the Pythagorean identity, which is also true. It's a relationship between secant and tangent. And then the last one stems from doing the same thing, starting with the unit circle equation, dividing through by y squared, and then simplifying, since y squared over x, this would leave me with x squared. The first one is x squared over y squared, which is the cotangent function squared. Y over y is 1. And 1 over y is the cosecant function. And this leaves me with the last of the Pythagorean identities, which you can see below. Anyways, these three formulas are always true, and they're a way of relating those particular pairs of functions together based on trigonometry. We'll actually look at these more a little bit later, but they are always true, as are all identities. We're going to be actually deriving and finding a bunch more identities in the next exam, which is another notoriously difficult subject within trigonometry. But all of these fundamental identities, the point here is that they're true, they're related back to the unit circle, and they exist just because of the definitions. They're just implications based on how it's fundamentally operated. So see y'all next time.